Hi, Assalamualaikum and a very good morning. So now we are in chapter 5, hydrocarbon, and we're going to focus on the subtopic of 5.2 alkenes, part 2 of the video. So in this video, we're going to show the preparation of alkene through the dehydration of the alcohol. The meanings of dehydration means we're going to eliminate water from the alcohol compound. Meanwhile, for C2 is the dehydrohalogenation of haloalkene. It means that we're going to remove hydro means hydrogen and halogen means that X. So X here can be Cl, can be Br, or can be F. Alright, so the removal of the hydrogen and halogen, hydrogen and halogen from the haloalkene. So by doing this, we can prepare an alkene. Next, we're going to write the mechanism for the C1, and we're going to also use the Saytzeff Rule in order to determine the major product for the elimination reaction explained by C1 and C2 here. So without any further ado, let us start. So there are two main types for the elimination reaction in order to prepare alkene. First, we have the dehydration of alcohol, where dehydration of alcohol means that we're going to remove H2O from the alcohol compound. Step number 2 is we can do the dehydrohalogenation of alkyl halide, which means that it removes the HX, for example HCl, from the alkyl halide. So the alkyl halides here means it refers to haloalkene. Okay, so it basically an alkene, for example CH3 CH2 Br. And now we're going to remove H and Br so that we can produce an alkene. Okay, so this is the general idea. So now we're going to do focus on the step A first, which is the preparation number 1, which is the dehydration of alcohol. So we're going to eliminate water from the alcohol molecule. For example, if we have the ethanol here. So when we treat it with concentrated H2SO4, which is the sulfuric acid, which acting as an acidic catalyst, and we're going to apply that reaction in a very high temperature, what we're going to do is we're going to remove the water from the ethanol in order to produce the ethene. So the H2SO4 going to react as the acidic catalyst, and the catalyst here can be changed using the phosphoric acid, so either one of those. Now we're going to come back to the Saytzeff Rule. So according to the Saytzeff Rule, in an elimination reaction, the major product is need to be the most stable alkene, where it need to have the mostly highly substituted alkene. So what is meant by this? So here, the most substituted alkene means it is the position at which carbon have a lot of carbon-carbon attachment. Okay, so the more number of attachment that they have, the more stable it is. Okay, for example, in this case they have none. Here got 1, here got 2, here got 1, 2, 3, here got 1, 2, 3, and 4. So one carbon attached with 2 methyl group, and here also attached with 2 methyl group or the carbon chain. So what we can say that the more highly substituted the alkene is with the alkyl chain, means it is more stable. So here is the most stable. Alright, so this is what meant by the Saytzeff Rule. Now we're going to do the reaction mechanism for the dehydration of the alcohol. So let's say if we have a butan 2-ol here, so 1, 2, 3, and 4. Because it have hydroxyl group, the name gonna be alcohol, and because it have 4 carbon, it's gonna be butanol. But now OH is attached at number 2, that is why the name is butan 2-ol. You will learn more about this in the next chapter for alcohol. So when butanol is treated with the sulfuric acid, which acting as an acidic catalyst at high temperature, they're going to produce 2 types of product. So we have Let's say if we remove water here, we're gonna get one product here, which is but2-in, or we can also remove from this side OH and OH here. So we'll get another product which is but1-in. So we will get major product here and we will get minor product here. And according to Saytzeff rule, we will get this reaction or this product to be higher because it is a much more stable and more substituted alkene. Alright, now by understanding this, we're going to do the reaction mechanism from the butan to all that we have shown just now, in order to form the major product, which is but2-in. So for the dehydration mechanism, it consists of 3 steps. Okay, so step number 1 is the protonation of the OH group. So the OH group here gonna be protonated. Maksudnya dia akan ditambahkan dengan proton, yang mana proton adalah H+. Okay, so we have butan-2-ol, and then we have our acidic catalyst as the reactant just now. Alright, so now we're gonna protonate this area, the functional group of OH here. So we're gonna bring an arrow to here, and this bond will be broken down, where this arrow gonna be passed into the HOSO here, which is the H2SO4. So H2SO4 can be written as SO3H and OH here. Okay, so this is the usual representation for the mechanism reaction. Okay, so the lone pair here will act as a nucleophile to attack the hydrogen, and then the lone pair will break and give the negative charge towards the balance of the molecule of the sulfuric acid. So what we're going to produce here, we will get the protonated alcohol. Okay, so just now we will plug it with an H, and we will also get our minus charge here because the 2 electron going to be transferred into here, and this will bring the negative charge. So this is what left at the end of the reaction. Okay, so this is going to use again at step number 3. So we will use at step 3. Okay, now we're going to bring this molecule and use that in step number 2. So for step number 2, as I'll draw this again here. For step number 2, we're gonna form a carboxyl ion. So in order to form a carboxyl ion, we need to remove water. Okay, so how can we remove water? Is by breaking the bond from the bonding from CO into the OH here, which is plus sign. So when we bring the lone pair, so what we're going to get is the carboxyl ion as well as water. Okay, so just now the O plus will have a positive charge, but when electron is being transferred to here, the plus sign is diminished and it will be replaced by the 2 lone pair here as shown in this product. Okay, and here because it's break apart, it's gonna get a positive sign because usually the carbon gonna have 4 bonds, right? But now it only have only 3 bonding, so it's gonna carry a positive charge because the formal charge have 4 minus 3, so equal to plus 1. Okay, so this is the step number 2, which is the formation of the carboxyl ion. Now for step number 3, we're gonna the carboxyl ion will lose a proton. So the way that it can loses the proton is from the step 1 that we have produced just now, which is our SO3H and O minus here. So the nucleophile will attack the hydrogen here, and this will break the bond in between the CH, and this will bring the bond to here in order to form double bond. Okay, so the carboxyl ion will now produces an alkene as well as the H2SO4 just now. Okay, Alright, so from alcohol, it will produce an alkene, which is our major product, and it will create back our H2SO4, which is the catalyst. So it clearly shows that the catalyst will not be used up in the reaction because it will be regained back at the end of the reaction. Okay, and here we can show that the major product is being formed. Alright. Now here is the summary of what I have shown just now. For step number 1, it is the idea of protonation of OH. Yang mana OH tadi telah ditambahkan dengan proton dan dia akan menjadi OH2+. Lepas tu, we're gonna break the bond in order to form carbocation, which is step number 2 is the formation of carbocation. So we're going to produce a secondary carbocation, and then O minus here can take up the hydrogen from this side, and this will create a double bond. So when this creates a double bond, a major product will be formed. At the same time, this O minus here can attack this hydrogen, which is on the side. Okay, if you were to expand the structure, so we will take this one and bring it here. So if we take this side, it will produce one butene, which is our minor product. Okay, but this is going to happen less likely. Okay, less likely to happen, and therefore it become the minor product. This will be happening more readily, so it will become our major product, which is 2-butene. Okay, and as for the mechanism just now, we only show it for the major product because usually for reaction mechanism, it only applies for major product, and that is why you straight away taking this hydrogen instead of taking this hydrogen here. Okay, so during the dehydration of alcohol, rearrangement can occur. So some of the primary and the secondary alcohol will undergo rearrangement in order to form a more stable tertiary carbocation. Let's say if we are starting with a secondary alcohol, as shown here. So this one is first, second. So the OH is attached at second carbon, so it's going to be secondary alcohol. So when water is eliminated from this side by treatment of the acidic catalyst and also high heat, two products will be formed. So we have first product here and we have second product here. So this is going to be the major product because it is a more substituted alkene. Meanwhile, this one going to be the minor product. Alright, so as what you can see here, at this carbon, it attached with 2 CH3. Okay, ada dua. However, it only attached to one now. So what really happened was the rearrangements are basically taking place because the CH3 here at one point of the mechanism gonna be bring out to here. Okay, and the shifting of the methyl group from this carbon into the next carbon is known as the migration. So we're going to look into that in the later slide. So basically, in order to explain the situation where the methyl group has been shifted, the step 1 and step 2 is similar to the previous example. So what really happened was, before it proceeds with step 3, the rearrangement occurs. So the less stable, which is the secondary carbocation, will rearrange to form more stable tertiary carbocation. So the rearrangement occurs through the migration. So migrasi kumpulan atom tadi tu yang mana methyl akan bergerak ke carbon sebelah dia, to the adjacent carbon atom in order to form a more stable tertiary carbocation. So because a group shift from the one carbon to the next, this kind of arrangement is often called 1,2 shift. Okay, so we have two type, which is 1,2 methyl shift, yang mana dia adalah pergerakan methyl group, or 1,2 hydride shift, which is the hydrogen movement. So now let us focus on this part first, which is the methyl shift. So the same concept as before, apply with, at concentrated H2SO4 at high temperature. Water will be eliminated in order to form a minor product, which is the less stable alkene, and we can also form a major product, which is a more substituted alkene. This is because there is a rearrangement occur where the methyl group is transferred to this side, and this is why we got CCH3, CCH3. Okay, you can imagine it as number 1, here as number 1, this one is number 2, and here going to be number 2. So one going to be attached with 2 methyl. So one of the methyl here going to be transferred to here in order to get 2 methyl. For number 2, they are okay with 2 methyl group with a star here. Okay, so we're going to look into the mechanism in the next slide. And this the process known as the 1,2-CH3 shift. So as I mentioned, step 1 and step number 2 is still the same. What happened during the rearrangement is before step number 3. So let's say if we have our alcohol here, which is 3,3-dimethyl 2-butanol, the lone pair gonna attack the hydrogen from the H2SO4. So this gonna protonate the OH group and break the bond in between the HO here. So what we're gonna form is the protonated alcohol, and our product that we're gonna form here is O minus SO3 H minus O minus here. So this we're gonna use it again in step 3, which is I already written it here. So from step 2, we're gonna remove the water first. Okay, so what we're gonna get is the secondary alcohol. So water is being removed, and so indicated here, and we're gonna produce a secondary carboxyl ion. However, the secondary carboxyl ion is not stable, so we're gonna do the rearrangement in order to form tertiary carboxyl ion, which is much more stable. Okay, so we're gonna do 1,2 methyl shift. Okay, so the name is 1,2 methyl shift because we're gonna bring we will indicate this as carbon number 1, and carbon number 1 from the protonated alcohol, the protonated carbon now bring to number 2. So that is why we call it 1,2 shift, and the CH3 gonna bring to that side here. Okay, so we're going to bring the CH3 to here, and this step is known as 1,2 methyl shift, where we're going to bring our positive charge into this side. Okay, so once we bring it to this side, this is going to become a tertiary carboxyl ion, which is much more stable. So once we produce a tertiary carboxyl ion, we're going to remove another hydrogen in order to make alkene. So we can remove this hydrogen here in order to make tertiary alkene, which is shown here. So if we were to expand the structure, we can bring our the negative charge to this side, and this is going to break the bond and put it to the middle of here. So that is why you will get C, 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 double C attached with 2 methyl group. Alright, so that's for step number 1. For this side, you can also remove this hydrogen here, where if you remove this hydrogen, you're gonna get primary alkene. Okay, so if you were to expand the structure, H, 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 and our lone pair or our negative charge can be used in order to attack the hydrogen, and our single bond here gonna bring it to this side, the center here. So this is gonna produce a double bond as shown as here. So this gonna produce a a minor product, and this step gonna produce a major product. So this clearly shows that the 1,2 methyl shift is important in order to create a major product. Alright, now we're going to focus on the next part, which is 1,2 hydride shift. Okay, the same thing as before. We're going to have 3 steps, but before it proceed to step number 3, it need to undergo rearrangement first. Okay, so we're going to draw again our alcohol here, and for step number 1, we're going to protonate. Okay, so X here is known as the 1-cyclohexylethanol, and now we're going to protonate our alcohol here, which is our OH group, and this is going to break the bond in between H and O, and this is going to produce the protonated alcohol. And PO3H2 here is also example of the acidic catalyst. So if you don't want to use sulfuric acid, you can use phosphoric acid. So here going to produce PO3H2 with a negative charge here. Okay. So this we're gonna bring it again at step number 3. Okay. So for step number 2, we're gonna break the bond and remove water. Okay. So we can break the bond and remove water, which is H2O, and this is gonna produce a secondary carbocation, which is not stable. What we're gonna do is that now we're gonna shift the hydrogen. So when we shift the hydrogen, it is known as the hydride shift. Just now you shift the methyl, so you're gonna be 1,2-CH3 shift, methyl shift, but now it's called as hydride shift because you remove hydrogen. Okay, so what you're gonna do here is you can bring hydrogen from this side into that side. Okay, so if you were to expand the structure, you will get H, CH plus, and also CH3. So once you bring the hydrogen or you shift it to here, you will get CH3, H, H, and then you will attach with the methyl group, the cyclohexane here, and this is going to be a positive charge as shown here. Okay, and this is going to produce a tertiary carbocation, which is much more stable. Now, for step number 3, we're going to remove hydrogen in order to form alkene. So, we can remove the hydrogen from here, where we take up this hydrogen, and this single bond going to break apart and place into here, and this is going to produce our product Y, and this going to produce a secondary alkene. Alright, so for dehydration of alcohol, you have the normal mechanism, and you also have the rearrangement mechanism. It's either methyl shift or the hydride shift. Alright, and this is going to be our major product. Now we're going to focus on the next preparation of alkene, which is the dehydrohalogenation of alkyl halides. So the alkyl halides here refers to haloalkane. Okay, before this, and according to the previous slide, we focus on the dehydration of alcohol, which is the removal of water in order to produce alkene. But now we're going to remove dehydro, which is remove hydrogen, and also remove halogen. So it refers to Br in this case. So we can remove hydrogen and we can remove Br here in order to produce this product. So if we were to remove here, we're going to produce major product. And if we were to produce from this side, for example, Br here and H here, we're going to produce a minor product. So this is called a major product because it is a much more substituted alkene, and this is the less substituted alkene according to the Saytzeff rule. So this carbon here going to attach with one methyl group, and here got two methyl group. However, in this case, the carbon-carbon double bond will only attach with one and only one methyl group here. So this is the more stable and therefore become the major product. Alright. Now we can also do the dehydrohalogenation of another product as shown here. So by applying the KOH and also ethanol under reflux, we can remove hydrogen and Br in order to produce an alkene. So in this first situation, we can remove Br here and remove the hydrogen from this side. Okay, so if we remove these two, we're going to produce this type of alkene. Okay, and if we were to remove the hydrogen from here, okay, so one of the hydrogen and Br is removed, we're going to produce another product here. Okay, so the upper one going to be our major product, our below one going to be our minor product. This is going to be the major product because it produces a more substituted alkene. So the carbon here going to attach with C and C, and this carbon here going to attach with another C. So it have three substituted alkene. However, in this case, it only have one because this carbon going to attach with hydrogen, and this going to be attached with hydrogen and hydrogen. So this carbon here only attached with one alkyl group. So this is the less substituted alkene in comparison to this one, which is more substituted. Okay, and for this reaction, we don't have any mechanism. Alright, so remember, you can remove hydrogen not from the same carbon of the halogen. Okay, you cannot remove Br and hydrogen from the same carbon. Okay, so you need to remove from the other part. For example, Br and H here. So you can produce a major product. You cannot remove Br and H from the same carbon. So this is not the correct concept. It needs to be yang jiran dia, adjacent carbon. Okay, so I think that's all for today's video. See you again some other time. Bye.